Just a quick video looking at calculating the mean and standard deviations from frequency tables. So for this exercise you will need a calculator, preferably a TI-84 because that's the calculator I'll be going through instructions with, but you can do these calculations really easily on Casios and other calculators, and the instructions are pretty much the same. So calculating mean and standard deviations, what we have here is we have a frequency table. Technically it has probabilities relative to a number set, but I'll go through that in just a moment. First off, I want to introduce you to these two formulae here. We have the mean and we have the standard deviation for a frequency table. So let's have a look at what the formulae actually say. First off, we have the mean, and the mean can be represented as having the independent variable and the dependent variable as a product. So that one times that one, and then add each one subsequent in the actual data set from the frequency table. So we end up with all of that divided by m, because of course you know that's obviously going to be the average. However, when we actually look at it in this context, we can simplify it to be just the sum of fi xi. So the sum of the product of fi xi. So simply, in this case, what we need to do, because this is a probability frequency table, we just need to go that times that. The independent variable times the dependent variable. Because of course, in the end, if we have all these added together over the same denominator, then when we have all those terms in the numerator added, then of course we're just, in the end, going to be adding just the numerator. So the denominator really doesn't matter in the end. Okay, so now what we've essentially got here, which I'll explain now in a bit more detail, is we have the number of minutes that a bus runs late by. Of course, the number of minutes a bus is running late changes every day. You could catch the same bus service and it wouldn't be going to the bus stop at the exact same time every single day. I mean, there'd be a little bit of variation there. So let's say that the bus generally runs on time or it runs late, it doesn't run early. These here are the probabilities of a bus turning up given minutes after it's meant to turn up. So if it's 0, then obviously we have a 0.54% chance of it showing up. At 1 we have a 0.26, then we have 0.15, 0.03, and so on. So obviously the later the bus service is, the less likely that the bus is actually going to turn up at that time. So it's most commonly probably going to be around about on time. But we can take the mean of this result to work out on average how late is it or how on time is it. So in order to do that, we're going to need a calculator, and we're just going to find the sum of fi xi. So the sum of this term multiplied by that term for all the terms in the frequency table. So let's go ahead and work out mu, the mean. So in order to do this, we go 0 multiplied by 0.54. Don't worry if you don't want to put that in, that's fine. I'm just going through the process. We have that times that so far, but of course anything times by 0 is going to be 0. So because of that, you don't really have to worry about it if you don't want to. And then what we do is we go plus 1 times by 0.26. Then plus 2, and remember to use brackets here, 2 times by 0.15, plus bracket 3, close bracket, bracket 0.03, bracket, plus bracket 4, bracket 0.01, bracket, plus bracket 5, bracket 0.01. Sort of repetitive there. And we don't have to worry about this last one, because how can we put in greater than 5? But look, the probability is 0, so we don't need to put it in, because of course it's never going to be more than 5 minutes late. Pretty good bus service. I wish we could have the same sort of thing here in Adelaide. But anyway, once you've got the product of that, and you've added all the terms in a frequency table together, again, you don't have to do that one, you don't have to do that one. I did that one, but that's okay. But you can't actually put that into a calculator, because you can't put greater than 5 times something. But you should get the mean, and mu should be 0.74. So hence, in context to the original table, based on this probability distribution, it means that the bus is most commonly, on average, going to be 0.74 minutes late. 0.74 minutes. Okay, so in order to change this into a term that we can work with, then essentially what we can do is, well, there's 60 seconds in a minute, so 0.74 times by 60 tells us that it's generally going to be around about 44 seconds late. 44.4 seconds late. That's a pretty good bus service there. It's actually running reasonably on time. And of course, you're going to have variation because of the traffic, but based on these probabilities here that someone may have collected from looking at the bus service and when it arrives, we can say, okay, generally it's going to be pretty much on time. I mean, 44.4 seconds isn't really something to get aggravated about. Half an hour, different story. Okay, so now let's have a look at the standard deviation. Okay, and everyone, I'm back again. Sorry about that. Just a quick break there. You won't notice it though because the video is tied into one. However, I've cleared off the board a little bit because it was getting a bit messy, and you may notice that I've been able to overcome the limitation of me sometimes writing over the board by drawing a line across there. I mean, I don't have a cameraman because my show's too low budget for that, but let's just continue and work with what we have. Okay, so what we need to do now is work out the standard deviation. So in the previous video we worked out the mean. Mean's here, mean is mu, and the mean is 0.47 minutes, and we worked out what that was in seconds, because if you went up to someone and they said, how long is it going to be for the noodles to cook, and you said 0.74 minutes, they probably have no idea what you're talking about. So it's good to work with seconds there. Okay, so you may remember standard deviation formulas. Up here it's the square root of the sum of pi, bracket xi, take mu, the mean, squared. And we have all this information here. So let's actually think through what we need to do. And what I'm going to do is, because standard deviation is a little bit complex, especially at first because you have all of this here, I'm actually going to write up on the board so you can follow along with me. And that's why I have this minuscule amount of space here. You may also notice in the break that I've added something. I wrote this question about the z-score, and I've got a new formula up here. Okay, I'll be going into z-score in another video. It'll be the very next video because it's our very next topic. But for the moment, I decided I may as well chuck it in there because it'd be interesting. Z-scores are quite cool, and it's a great way to finish this video because I've probably got an extra bit of time, and it'll give you a heads up for what's to come. So, with that in mind, and me no longer jumping all over the place, let's go through this. So we have the square root, and we've got a long square root here because we've got a lot of data to put in. Okay, so follow along with your calculator too. Take the mean, and then that last expression squared there, and we can just put brackets around it if we want to make it a bit neater and more mathematically correct. And then we do the rest for all of them. So hopefully you can see what I've done there. All I've gone is pi out the front, then I've put the mean in, not the mean, sorry, xi first, subtract the mean squared. So it's pi, bracket, xi, take the mean, and then it's the xi take the mean that's being squared in that term there. So now what we can do, after we've got our heads around that, hopefully you can see how I just pulled the values across. Sorry if it's a little bit confusing. But what we do on a calculator is we go second function, the square root, and we make the entire thing a square root, and we put in brackets pretty much to isolate every term with 0.9962 minutes. So again, if you haven't put it in correctly, just think about how you're allocating the brackets and how everything's dispersed amongst the equation. But again, just plug it in on that form, and it will take a bit of practice. Okay, so after this, let's have a look at the z-score and what it actually asks us for in this question. So calculate standard deviation, so sigma equals, and then we have 0.9962 minutes, as I said before. We could put that in seconds if we wanted to. 0.62 minutes late. So let's have a look at what this means. The z-score asks, essentially is a measure of how many standard deviations a value is away from the mean. So remember in the first video I showed you the basics of normal distribution, that 3-part series? that we have 3 standard deviations commonly within the mean? Yep. Well, a z-score, if it was 1 standard deviation to the right of the mean, it would have a z-score of 1. If it was -1, then -1 standard deviation, so 1 standard deviation left of the mean, then the z-score would be -1. It tells us a position relative to standard deviations from the mean, where a value lies. Okay, so in this case, the first question is very simple. It's a very abstract number. That's because I've purposely made it become a whole result. In some cases, your z-value could be 1.234, for example. It could be a value like that where it is not perfectly lining up with a standard deviation position, like it will be with 2 minutes, because if we know that the standard deviation's going to be like that, then we know that it isn't going to perfectly line up. So we know that the mean is, of course, as I said before, 0.74 minutes late. And we know that 1 standard deviation is going to be a difference of 0.9962. And we can add those two numbers to work out the position, or how many minutes late an object is if it's 1 standard deviation from the mean. So 0.74 plus our standard deviation of 0.9962 gives us 1.7362. So 1.7362 minutes late. Hence the z-score for this problem here, the z-score we can easily write as being 1. Z equals 1. The critical probability, which is z, equals 1 because it's 1 standard deviation right of the mean. This is a positive direction if it's on this side of the mean, to the right of the mean. Remember, think about motion concepts, they're positive and negative. And if it's to the left of the mean, then it's a negative z-score. But, as I said before, it may not be lined up directly on that part. And in order to do that, we use this formula here that I'm going to introduce. And that's the z-score formula, the critical probability formula. And again, we just plug in the value for what we want. So in this case, 2 minutes late. So 2 take mu over sigma. It is really that simple. So in order to do this, let me just first answer this question and write it up a bit neatly. So, this first one here, I'll write it to the side. Z equals 1. The critical probability equals 1. And 2 minutes late, let's have a look. We have Z equals X, where X is a value like 1.3773 or something like that, is a value along this distribution here. Okay, and take the mean that we were able to calculate over sigma. This means that Z equals, and in this instance, what we have is we want to know 2 minutes late, so it's 2. Take mu, and mu is 0.74, and it's all over sigma. And sigma, in this case, worked out as being 0.9962. Hence the z-score for running 2 minutes late. So how many standard deviations is a 2 minute late bus in terms of the distribution? That's essentially what the z-score is we go into our TI-84 calculator, we go alpha, y equals, press 2, then delete the square out the front, and we just go 2, take 0.74, that gives us a fraction bar, we put that in the numerator, and then we divide that by the denominator, and we should get a positive result, because obviously 2 minutes is further along the distribution, 1.7 minutes late, and we're looking to the right of the mean, so we get a result of 1.265. So the z-score is 1.265. And 1.265, that means that it is 1.265 standard deviations to the right of the mean because it's positive. Okay, so we know where it roughly lies. If there was a bus that was running 2 minutes late, we know where it fits onto our probability distribution, and we could see, okay, that's where it is relative to the mean, so it's either a rare occurrence or not really a rare occurrence. It gives us an indicator. If this value is close to 3, for example, then we'd know, oh, it's a rare occurrence. The bus generally isn't that late, because it's 3 standard deviations, so the only probability of it being greater than 3 standard deviations is 0.15%. So you know it would be a rare occurrence. But it gives us an indicator. That's what the z-score does. It tells us how many standard deviations it is away from the mean. And you've probably seen... Okay, more on z-scores in another video. That's another topic. But hopefully this has covered everything, all good. Any questions, post them below. That's it for this video. Thank you for watching and listening.